Howdy everyone, Nir Regev here, and today we have the pleasure of hosting Dr. Alon Arad, a scientist in computational mathematics and AI. Alon earned his PhD in applied mathematics from the Australian National University, where he developed advanced image processing tools and numerical algorithms for various applications. His career includes roles as a research physicist at Royal Dutch Shell and a joint visiting fellow at MIT Department of Mathematics, focusing on high-performance mathematical techniques for the oil, medical, and defense sectors. Currently, Dr. Arad serves as the director of AI in Walmart, where before that, he was the director of AI and analytics at Certified Collectibles Group, a Blackstone portfolio company. His research contributions include machine learning, image processing, and in the last few years has focused on end-to-end deployment for various machine learning applications. Dr. Arad's extensive experience bridges academia and industry, making him a leading voice in applying computational techniques and AI to solve complex real-world problems. Thank you for being here, Alon, and I am very, very happy to have you here.
Hello, Dr. Nir. Thank you for the kind introduction. So very happy to be here and have a chat with you about everything around vectorization and personalization. I'm excited for it.
Okay, great, great. Yeah, me too. I'm very excited about this. And again, thank you for being here. And as always, we are going to start with a short, kind of 20 minutes ish presentation about a very interesting topic. And this time, Alon is going to teach us about vectorization and personalization. And then we will, after this lecture, it will be more like a free type of conversation between Alon and I. And without further ado, Alon, please take it away.
Okay, thank you, Nir. I will share my screen 1 second. Here we go.
Yeah, I can see it.
Okay, you can see it. Excellent. So today we'll be talking about personalization, recommendation, and search, and the underlying kind of mathematics that can be applied to all three subjects. And I'm pretty excited to talk about this. So the first thing is you'll see this table of contents. I kind of picked this up when I was a university lecturer. I kind of constantly feed back the table of contents throughout my presentation. That way it really helps my audience focus on what I'm talking about. So you'll see this a few times throughout the discussion. But we'll start with first an introduction. What are we trying to solve? We'll talk about vector-based architecture. So how everything can be vectorized and what can we do with these vectors. Subsequently, this kind of naturally leads into vector databases, kind of like new cutting edge technology that allows us to leverage AI and do a whole bunch of stuff. And then I'll kind of change gears a little bit. And at that point, we could basically say we could already build a recommendation engine and so forth. But what can we do that's a little bit better with matrix factorization? And one of my favorite topics, reinforcement learning. I kind of will wrap it up with what are the challenges, and then we'll just have a discussion and go from there. Cool.
Excellent.
So we'll be talking about search. So what does search mean? If I have a product, whatever that product is, it could be an image, it could be a video, it could be a product, right? How do I find something that's similar? Personalization, what does personalization mean? Is if I have a very large group of people, how do I identify characteristics that are similar between all of them? And then finally, recommendation. So recommendation is, and there's an overlap between all of these three things, but recommendation is essentially, I can recommend something to a group of people. Either I can do it through personalization or I can do it independently. Now, one caveat is that there is not one way to solve this problem, right? There are many, many different ways of solving this thing. But I will be exploring a couple of different methods. The methods that I've chosen I think, are very scalable to millions and millions of people and very scalable in terms of technology. So that's why I'm choosing these particular methods that we'll be talking about today. Okay, let's start with vector-based architecture. Everything can be vectorized. So here you see two kind of like silly cartoons, right? You see a text and you see an audio, but essentially anything can be vectorized. And what do I mean by that? Let's take a very, very simple example. And I really like to use images because I've done image processing for a very long time. And let's take the standard, let's take a very bad image, 1000 by 1000 megapixel image, which is very bad at the moment, right? It used to be back in the day that was amazing, but nowadays that's like not a very good picture. The very simplest way to vectorize this image is if, let's say 1000 by 1000, I start with 0, 0. I take the RGB value, for example, at the very top corner. And that's my first element of my vector. I take the average of the RGB and I move across. And every time I go across, that's one element down on my vector to put in that specific floating point value, right? And as I get to the end and I get to 1002, that's my 1001 component of my vector. So that's a raster scan through my image. And essentially, I build up this vector on the right-hand side, right? And this is a very simplistic way of building what you call a vector or an embedding. I like to use these terms interchangeably. But now these vectors or embeddings are incredibly large, right? They're even 1000 by 1000 image, which is like tiny by today's standards, is a vector of 1 million, right? And so what can we do, right? So what we have to do is compress these images or compress this information somehow. So we compress it with a model, right? So the model is essentially, I can use a Fourier decomposition, I can use a wavelet decomposition, but the cutting edge technology nowadays is to use a deep neural network or some sort of neural network to essentially take something and create like a compression and create a vector, right? So a neural network is a higher dimensional space and it finds some sort of lower dimensional embedding that represents that vector. And you can do the same thing with user information or even text. You can imagine for a document with text, a very simple embedding would be just give me the frequency of words. So if a word appears 10 times, that's the first element of the vector, and so forth and so on. That is a very simplistic embedding, but we can come up with more and more complex embeddings that capture more information. Similarly with audio files, right? I can take a Fourier decomposition and again, item description. So all these things essentially have a vector or embedding representation. The key is which embedding or which way do I create the vector, right? So that is the complex part of this whole mathematical situation. What do I do? And for example, with user information, what can I do? I can embed like their age, their sex, their height, their location. Again, that's just a vector. And those vectors could be of any length, right? It could be length 3, length 5, length 1,000, or even 1,000,000, as we discussed. But essentially, that is the mechanism of taking any sort of unstructured information or even structured and creating a vector out of it, which is now something that we can leverage mathematically to do operations on. So what is the point of all these embeddings? The point of all these embeddings is to capture relationships between objects, right? And so what does it mean by relationships? Here you see a simplified visual of a neural network, for example, a transformer embedding, where I take a bunch of words and specifically now I look at bananas and apples and strawberries in a natural language kind of setting, and they all can kind of get grouped together based on this specific embedding. I haven't told you what this embedding is, but you can leverage one of these Google or Hugging Face transformers, and you'll see they will naturally cluster together. But what does it mean to be close to each other? Or what does it mean to be a nearest neighbor, right? We haven't kind of touched on that. So the embeddings will put things close together, but we have to mathematically define what does close together mean. So in mathematics, there's a bunch of measures, right? There's a way to measure distances. So mathematically, we can call L2 norm, L1 norm. L2 norm, by the way, is just the Euclidean distance. Everything that we're all used to is this squared plus this squared plus this squared under the square root sign in 3D space. But you can imagine higher and higher dimensions, this gets interesting and complicated. Sometimes it's better to use like a cosine distance. And the Hamming distance is particularly powerful for a lot of machine learning because, you know, you have categorical data, so they're not necessarily floating points, and you need a way to measure ones and zeros, like how different objects are, not necessarily like distances in the exact sense of the word, right? And so for Hamming distance, right, super useful for categorical data, super useful for basis like biological systems like ATGC, where you have to look at differences between these kind of categories. And by the way, each one of these topics takes like a whole semester to go through. So I'll only be giving today like very highlight information. And as we progress, perhaps we can do a lot more of these discussions in the future. So,
So
um,
Alon,
you know,
Alon, a question. So these distances are a measure of similarity between classes?
they could definitely be right, and they're definitely a measure of similarity, absolutely. And the way you capture that similarity is these neural networks or whatever it is that you choose, these embeddings will either a specific embedding will group them all kind of close together or further apart depending on which embedding you choose. But then you still have to pick a way to measure similarity, exactly a measure of how close they are to each other. Exactly correct.
Okay, and another question that I had, maybe for previous slide, is the extraction of embeddings equivalent to what we used to call feature engineering in machine learning?
It could be, but it could be more complex than that, right? So an embedding could be as simple as a Fourier decomposition, and so that's in a way you can call that feature engineering, right? Or the neural network
Yeah,
automatically creates some of these
great.
dominant features, right? So it's like some of these things will create the features for you, but feature engineering is like a little bit of a different topic, but if you like, it finds the dominant features in these objects.
Gotcha. Thank you.
Yeah, welcome. Um, let's see. So this is a particularly interesting slide. I wanted to add it in there. So now we have a way of measuring distances between objects, right? So we have some sort of measure. We have a whole bunch of ways of creating these vectors. And here, my own personal anecdote, before I really knew about vector databases, which we'll talk about in a minute, how can we find things that are close together? So in my younger days, I was very interested in compressed sensing, right? And there's this idea of compressed sensing where there must exist some sort of lower dimensional representation of something. So you typically use the L1 norm, and again, we can talk at length about the L1 norm, but not today. But essentially, you can imagine if I have a database of facial images, right? And now I've used Fourier decomposition or wavelet decomposition or a neural network to create the embeddings of all these faces, right? And I smash them all into a matrix. This is my matrix A. And I have a new face, vector Y. And I want to find out which linear combination, right, which faces or my nearest neighbors will allow me to kind of find the correct vector that represents in my database, right? Because I can take my image 3 or 4 times and your image 10 times and so forth. The idea is that I will naturally get the linear combination from the solution using the L1 norm minimization. I can't use the L2 norm because that will give me almost like a cloud or mush of all the combinations of vectors. But the L1 norm will give me the most sparse combination. That's what you see X. X is those that linear basis function that will give me the right-hand side vector. So this was my original way of finding nearest neighbors in a very large kind of database. But the problem is this doesn't scale, right? If I have to do this millions and millions of times, I have to do this computation. It's a lot of compute to be able to do this in a very large scale. So just a side anecdote, just for fun. Next. Cool. So what can we do that's better, right? So I know in your other podcasts, you have a very cool, and I highly recommend it to everybody, a discussion on k-means and k-nearest neighbors, right? So you can start using these more uh, different algorithms that are very applicable to this solution, which will automatically, now I have a whole bunch of these vectors. I can use k-means, k-nearest neighbors on categorical data to very quickly find the clusters. Or even more recently, right, there's approximate nearest neighbors, and one specific algorithm that everybody nowadays uses is this hierarchical navigable small world solution, which will automatically, like for example, you can see on the top left, it will give me all those trees, right? Redwood, palm, and willow very quickly in a billion vectors, right? And that's what we're really kind of aiming for in terms of the solution space. So this naturally leads us now to what is a vector database, right? And so in a vector database, what can we do with a vector database? So again, we can use approximates near neighbors, we can use KNN, k-means, and so forth, but that's still a lot of compute to constantly do that over and over again. Every time I have a new vector, how do I find it in a billion vectors? And what vector database give us is essentially a very programmatic way of doing this very quickly and very efficiently, right? So they automatically group all the items together based on specific indexes. So I can have different norms where it will automatically say, this is the grouping on cosine norm, on L2 norm, L1 norm, Hamming distance, right? And then it has caching. So if I ask the same query multiple times with a new vector, it will automatically give me the answer. It has a bunch of other cool stuff. And some vector databases even have the embeddings pre-chosen for you, right? So I don't have to go and look at Hugging Face for a million different embeddings. It will say, hey, this is probably the best embedding for images. This is probably the best embedding for text and audio, and even for time series data, for example. And now we really have all the components we need for search, right? Because if I have a million or a billion images, I've created an embedding for all those images. I put them all in the vector database, and I have a new image or a new description of an image, and I want to say, give me all the items that have like a red dress that's like a size small and so forth. And then very quickly, it will look at the cosine distance based on images or text and so forth, and it will give me the right answer. And in fact, I can do even more than this now. I can build a recommendation engine. So if I can build Spotify almost, right? So if I have a specific music that I like, right? And I create an embedding either with a Fourier decomposition or a neural network again, and I'm listening to it and I like it, and I say, give me all my 5 nearest neighbors, right? It will automatically give me the 5 best songs that I can find very quickly, right? So this works, and I can query this thing a billion times, and I think within seconds you get the right answers, right? And it's very, very, very scalable to lots of people. So I can do now search, I can do recommendation, and in fact I can even do personalization, right? Because now I can take a whole bunch of users, embed their behavior in some way, and I can say, here's a new user with this kind of descriptors. What group does he belong to, right? So in some ways, we can just finish our conversation, but I think there's so much more to explore in different mechanisms that I think we will probably continue a little bit more.
Yeah, very interesting. I have a question regarding,
Yes.
you said that the one norm method is the penalty there didn't scale. Can you elaborate on that?
Yeah, absolutely. So it's not exactly so as these matrices get bigger, right, and as the vectors get bigger, and especially the matrices, that's the biggest problem because now I have a billion users or a billion faces. I believe it's something like and log n operations and so forth, which is still quite a lot. And when I have to do this 100 million times, especially as I'm serving 100 million users for a company like Walmart and so forth, it becomes very problematic to use something like that, right? And so a vector database is probably not as mathematic. I mean, it's still mathematically interesting, but it doesn't have the L1 norm kind of like decomposition, which I'm still very biased towards. Then it requires a lot less computation. So that's the nice piece of that.
Gotcha. Thank you.
Especially with the indexes, and I guess that's the trick is the indexes in the vector database.
Yeah, understood. Thank you.
You're welcome. Cool. So now let's talk a little bit about what can we do even more with matrix factorization, and one of my favorite topics, reinforcement learning. So let's see. So let's pick 2 case studies, right? So let's say personalization is done. So I have a billion customers. I'm narrowed it down to maybe 100,000 customers, but I want to segment those customers. And let's say I have 2 specific use cases. One Bless you. Uh, One is when you have a very, very sparse matrix, and this specifically relates to something like Netflix, right? Where I have maybe 100,000 users, and I maybe watch like 2 or 3 TV shows per user, but the rest of the, if you like, the columns in that table are zeros or empty. So how do I fill out this table, right? And the other one is a little bit different, more probabilistic approach, where maybe I have like 3 items and I have 100,000 users that I know are susceptible to buying these 3 items, but I want to rank them based on what's the best item to present to my customer, what's my click-through rate, or what's my higher probability item that people will buy. So these are the 2 use cases that we can talk through. I know I'm a little bit over. I apologize for that.
No, it's perfect.
Those cool. So let's use a very simplistic kind of table here, right? So I have 5 customers and they buy vegetables, fruit, sweets, bread, coffee, right? And the idea is, excuse me, we want to do what's called a non-negative matrix factorization. Now, this method breaks up my matrix V into 2 matrices, W and H. Now, as an interesting anecdote again, one of my PhD students did a lot of work on non-negative matrix factorization for the oil and gas industry. We did some really cool stuff around identifying NMR signals and automatically clustering things. But here we can use it for personalization. But the mathematics is super cool because it applies to so many applications. And so what are we trying to do here, right? So we're trying to decompose this matrix V. It's highly ill-conditioned. What does ill-conditioned mean? Is that as I do these operations, the singular values, and then we can talk separately about what those are, but they're very, very close to zero. So all these inversions, they constantly blow up on you. So even though I'm simplifying everything here, the actual underlying mathematics requires regularization and a bunch of other cool things. But essentially, we want to have the dot product between matrix W and H as close to V as possible, right? And it makes sense. The Frobenius norm is, and that's the L2 norm of the matrix, well, Frobenius norm specifically of matrix A is as close to zero as possible. And so let's see what that actually looks like. I've done all the maths for you guys, and we'll just see the numbers. Cool. So here we have on the left matrix W, to the right matrix H. Bottom left is reconstructed matrix V, and just for reference, the original matrix V. Okay. Now we pick some headings: fruit pickers, bread eaters, and veggies. Those are arbitrary, right? I could have put any headings in there, but the reason I picked those is because you can see the dominant kind of like values are for fruit in the first column is 1.93, and then for example for veggies is 2.74. Now if we look at specifically matrix H now, we can kind of like identify for specific users what they're interested in. Like for John, I can see he almost exclusively is a fruit picker. And for Peter, maybe fruit picker and veggies and so forth. And as a recommendation, I can look at reconstructed matrix V, and I can say, if I just go from highest to lowest, those are the things that I would recommend to Alice, right? So first I'll go with fruit, then I'll go with bread, and so forth and so on. And that will be my list of recommending stuff to folks. Now, at first, people might say, that's not that interesting, right? Because I can see from their sales data that, 2.84 for fruit is very similar to 3. But we'll go to the next slide and we'll see what's interesting about this whole thing. So specifically, let's look at coffee, right? So coffee now has 2 dominant values, one for Peter and one for Jennifer. Now notice for Jennifer, she had 0 in the original matrix V, right? And now we know that we can recommend coffee to Jennifer and Peter because we've now populated, as we were talking about, like that Netflix problem, we populated the zeros when they naturally fit into the system, right? And you can actually see this actually makes a lot of sense. So Peter, and you can probably do this with a vector database as well, but Peter, if you look at the actual numbers, has very, very similar numbers to Jennifer, except for the coffee in the original matrix V, right? And so this naturally kind of came about and populated the matrix, reconstructed matrix, and gave a good recommendation.
But I have two questions here. So first,
Yes.
can you explain why does it make sense to, in this case, to recommend to Jennifer coffee?
Well, I guess from the engine itself, it kind of just said, hey, the behavior of this person is very, very similar to the behavior of Peter, right? So
Right,
that's
right,
why these numbers kind of come out
right.
naturally
Got it.
from
Got
this
it.
non-negative matrix
Got
factorization.
it.
Yeah. Yeah.
And second
And
question, these numbers in the left corner, down left, this is the matrix V, right?
yes,
What
reconstructed.
is what does zero and what's the maximum number here? Is there a maximum?
There are no maximums, so
Okay.
it's a little bit funny. It's not exactly eigenvalues and so
Hmm.
forth, but they're kind of like highest to lowest, right? And so
Hmm.
the higher the number, the more you kind of say this is the more dominant kind of feature
Yeah.
for this person. And the reason it's non-negative, right, is kind of like least squares. If you
Yeah.
add negatives, all the other values go crazy.
Yeah.
And
Yeah.
so also the non-negativity is also adds to the ill condition part of the computation. So
Right. Right. Right.
yeah.
Very cool. Very cool. Thank you.
So now we will talk about reinforcement learning. So
Mhm.
a completely separate idea, but also very incredibly interesting. So we'll shift our focus now to promotions, right? So I want to promote a handful of products. I mean, we kind of did that with coffee. We kind of find the vector that dominates for coffee. That's why I had Jennifer. But let's say we have now groupings of people, and maybe we have three different items that we want to figure out what's the best to recommend to that group of people. And we will leverage Bayesian methods and Thompson sampling, two very
Mhm.
cool. So I'll give you a little bit of background and then I'll show how to do this. Now, I would say I'm using slot machines because that is the standard way where everyone introduces Thompson sampling because it came from this idea of the multi-arm bandit, right? Where
Mhm.
I have like three slot machines. I don't know the distributions of the payoff. I'm trying to figure it out by playing one or the two or the third slot machine. And I want to make sure that I'm exploiting this thing as much as possible, right? Because I don't want to waste money playing these games for too long. I want to
Yeah.
maximize
Yeah.
exactly the same idea.
Hmm.
So the simplest strategy is essentially A/B testing, right? I have three different items, three different slot machines. I can simply say, give 1,000 to the first group of you, or give 1,000 to 1,000. Sorry, show the first slot machine or the first ad, for example, to 1,000 users. Show the second ad to another 1,000 users, and show the third ad to another 1,000 users. So those are three different ads or three different items, and then you just look at the frequencies at the end of the day, and that's the frequency approach to solving this problem. The problem is this is very expensive, right? So let's say slot machine two is the most dominant. For example, I wasted 2,000 approximate like ads in showing to the users, and it's the same as a slot machine. I played 2,000 additional games to be able to see my payoff, and I want to maximize my payoff in some way.
Hmm.
So we leverage the beta distribution. You can also leverage Gaussians or a bunch of other ones, but in this particular case, we'll start with the beta distribution. The beta distribution is very simple. It essentially has two outcomes, success and failure, and we can see what it looks like. I have a few diagrams of what that looks like in the next slide. And then we will use the Thompson sampling to play between the different slot machines, right? So we assume that each slot machine has a beta distribution, and if it's successful, it's a +1 to the alpha. If it's not successful, it's +1 to the beta. But we will use the Thompson sampling to jump between the two. And the key concept is again is the more successful the machine as you start playing it, the more you want to pick that machine to exploit your maximum payoff, right? You don't want to play things that as you play are not giving you a very high payoff.
Hmm.
So what is the beta distribution? The beta distribution is a bit of a funny It's called the probability of probabilities, right? And that's essentially, you can see that as you start playing, the variance of this distribution is very, very high, right? And so they're all 2/3, right? Every one of these things are 2/3. But as I play more and I gain more and more information, the variance decreases and the mean stays exactly the same, right? And so this is very important for the Thompson sampling approach, right? Because this variance allows us to play between the different games in a very efficient way, while maximizing our returns. So let's play this game, and we'll walk through the whole system just to see what the outcome is. So we will start with the uniform beta distribution. Alpha is 1, beta is 1 for all 3 ads, all 3 slot machines. And we will play the game. So let's play. When we play, you see the stars. The stars essentially gives us slot 1 was 0.2, slot 2 was 0.7, and slot 3 was 0.5. Cool. That means we pick slot 2 to play our game.
Mm-hmm.
We pick slot 2. Now, we play slot 2. Now, slot 2 happened to pay off or happened to be successful. So that means in the equivalency of the user, you showed slot 2 or you showed ad number 2 to the user and they actually clicked on it. Equivalently, we could have easily had the ad not picked, right? And then the beta distribution would have been updated to beta 2, alpha 1. But in this particular case, alpha got increased by 1 and beta stayed as 1. And so what you see is that the beta distribution, the mean, moves from 0.5 to 0.667, right? For example.
Mm-hmm.
And so now we update. Now we update our prior, posterior. You can see slot 1 or add 1 and add 3 stay the same, but add number 2 gets updated. And so we play the game again, right? And now the mean shifts a little bit for slot 2. But for slot 1 and the variance, obviously, but for slot 1 and slot 3, they stay the same. So we play the game a couple of times and then we see what happens. So after a couple of tries, this is what the distributions look like, right? So on the left, it happened that slot 1 and slot 3 got picked quite a lot. And so you have alpha is 8, beta is 3 for slot 1, but the mean is around like 0.75. For slot 2, it wasn't played very much. So alpha stayed as 2, beta stayed at 2, but the variance is very, very large, right? And slot 3 was played quite a lot, and the beta now was very high. Distribution shifted to the left. So what will probably happen now as we continue to play this game? Most likely, slot 1 will get picked, but there's a very high probability that slot 2 will get picked as well, right? Because of that variance, we can be well above 0.75 as we play the game. So the variance allows us to play things that haven't been exploited. So we have a way of saying, things that haven't been explored very much. There's a natural mechanism in Thompson sampling to pick that distribution, whereas now slot 3 has been explored a lot. It doesn't get picked at all, right? And so now the next winner will be either slot 1 or slot 2. I think in this particular game, slot 2 was actually the best winner. And you'll see that. And the cool thing is, you can show mathematically that you need a lot less than the frequency approach, right? Where I wasted a lot of money or I wasted a lot of ads to show the customers what they were looking for. And this is a much better way of doing advertisement nowadays.
How much less?
I don't have exact numbers, but it is very significantly less. It's definitely worth the effort to implement this solution.
Yeah, this is fascinating. I didn't. This method, it's the first time I've seen it.
It's very cool.
It makes sense, but it's very cool. Yeah.
Yeah, it's very cool, and you can do it with like so many other things as well. But there's definitely cool, and in fact, people now do it even for A/B testing for clinical trials, right? It's not just retail applications. There's so many other clinical applications and other applications that you can leverage this for. And in clinical, obviously, you don't want to give bad drugs to people. You want to give them only the best drugs. So it's very useful. And let's talk about what are some of the challenges, right? And I've seen this now in multiple companies. So let's start with the software challenges, right? So the software challenges, and this is maybe the biggest break between, I think, in my experience, academia and industry. And I actually maybe plan to go back to academia next year and maybe teach at University of Arkansas because I really love teaching anyway. But just trying to bring some of these back to the academic setting where, a POC is great, but going from POC to production is very difficult. And so there's a lot of things missing between a POC and production. And I typically tell people it takes 3 times longer to build a production system than just the original POC. So if you spent 3 months building out a POC, it will probably take you a year to build out the full production system end to end. In a sense that you need unit testing, you need error handling, logging, good programmatic deployment, right? So there's the ML ops system involved. Now, you can certainly cut this time as these tools get better and better for deployment and for programmatic solutioning and so forth. But a POC is just a lot easier than a production system. I'll say that. And I think in a lot of industries as well, not just in academia, there is the misalignment of expectation. And I think it's very interesting to be in both academia and industry and see how people approach this solution.
Yes.
On the math side, there's also problems, right? As we discussed, non-negative matrix factorization is very sensitive to noise. It has a lot of scaling issues, right? Because it uses a bunch of regularization techniques, and you have to really understand what you're doing. Similarly, with embeddings, there's infinitely many embeddings that you can pick from, right? And if you choose the bad ones, then those clusters that we saw, they're not clustered, right? And so as soon as I use a vector database or I use some sort of k-means or KNN, they don't cluster. I don't get anything of value from my system. And so very interesting to put all this stuff together in industry setting.
Yes. And that's your job, right, Alon?
That is exactly right. That is my job. My job is to put these things into production, train my team, and get everyone excited about AI and production systems.
Yeah.
And that's really it, Dr. Nir. So we can have just a general discussion now.
Yeah, absolutely. First of all, that was fascinating. So thank you for that. I think it will be very, very beneficial for the listeners of this podcast. As you know, my background is not in recommendation systems or these sort of applications. It's more sensor type statistical signal processing and machine learning and AI there. And I can tell you from a point of view of a person that has an equivalent job in the industry of taking radar systems, say, or computer vision systems, and first doing a proof of concept, but then taking this proof of concept all the way to something that is working reliably, automatically, or let's say pseudo-automatically sometimes in the field, is the gap between these two is enormous. And as you said, it's times 3. Sometimes it's even a more order of magnitude more time and more effort. It's not only time, right? That is needed to actually putting something that works in the hand of a customer. And I can imagine that in a company like you worked for, Walmart, when the scale is hundreds of millions maybe, is very, very, very complicated and requires rigorous testing and verification and validation and all this stuff before you actually do anything on the actual users. So kudos to you, Alon. And I think so. First of all, thank you for this wonderful, fascinating presentation. I know it enriched me as well, and I hope it will also enrich the listeners. And second, I think that the industry now need, that's my personal opinion, need people that understand, have very strong foundation of the mathematics behind everything that we do, as well as the knowledge and know-how how to take this mathematics from paper to the end user. And as you said, it's everything looks fine and dandy on paper, but it needs people like Dr. Arad here to take and actually deal with all the corner cases, because, as he said, it's ill conditioned. It's all the problems that we're dealing with in real life are ill conditioned or ill defined, and that's the beauty of taking mathematics from paper to the to production level. And thank you for bringing this up. I think it's across a lot of different uh, disciplines, and not only recommendation system data science type.
Absolutely.
So
So I was previously in radar systems a little bit myself, and like you said, and oil and gas, right? Everything is ill
yeah,
conditioned. Everything has an inverse
everything.
problem. Every time we do reconstruction, we have some
Yes,
sort of sparse data, and
yes,
yeah, it's really fun to do the mathematics around these things.
it is. It is. Yeah, yeah. Okay, so let's move on and strike up a usual type uh, conversation between us two. Please, you can call me Nir from now on. And I think that a very interesting, uh, very interesting aspect is to understand what brought you to where you are right now, Alon. Like, did you know as a kid that you want to be a scientist, or something sparked your interest in science, or a mentor, or some family member? How did you go about growing up from I imagine, very curious kid to being a scientist, and of all places in the industry, as well as touching academia?
That is a interesting question. So definitely there was an essence of Brownian motion. I think randomness in the whole thing.
Yeah,
So certainly as I was growing up, I loved mathematics. Right, I was like I was watching math videos and reading like the advanced textbooks from a very early age. And one of the things that piqued my interest actually in high school was a dissertation by Eric Drexler around nanotechnology. And I read this and I became obsessed. I was like, I am going to make nanorobots. And no one in my family was really a scientist. There was doctors and so forth, but no one was really a scientist. And so I didn't really know what to expect as I came into university. So I was like, by the time I finish undergrad, I'm going to make nanorobots, right? That was my expectation.
yeah,
And I was not anywhere near close to that. But I started exploring some physics, some mathematics. And what I realized is very quickly my passion more veered more into the mathematics than it did anything else. And I think specifically computational mathematics. So I really started getting more into that. I did a master's of actuarial studies for a while just because I started to get into insurance and finance and learning about financial instruments. And
mhm,
then I guess it was kind of strange because my initial goal was to kind of move into hedge funds in the US. And so everyone
okay,
said, go do a PhD in computational mathematics. And I did my PhD was fantastic. So my supervisor let me do whatever I wanted. And I started, one of the things that you'll find about me is I'm never not curious, right? So I always
yeah,
reach out to various professors. So I started reaching out to professors from Max Planck Institute, Munich Technical University, MIT. And because they liked my curiosity, they invited me over. So my PhD started at ANU. Then I went to Max Planck Institute in Germany. That was crazy. We did blackboard, like math on a blackboard, and we had tea outside. It was really good fun. And
wow,
then afterwards, I met Professor Alan Edelman out of MIT, and then he invited me over to do computational math over at MIT. And it was very different, and we had a lot of fun over there. And I think subsequently to that, I kind of didn't really care for the hedge funds anymore because I met this really great mentor at Shell. His name was Dr. Dunayevsky, and
mhm,
he was like that became almost like a mentor internship relationship, right? So he really taught me in 5 years at Shell the most math I've ever learned, even after my PhD, right? So
Yeah.
he was really like, "Hey, you don't really know anything," and I was like, "Man, I need to impress this guy,"
Yeah.
and really studied even harder and had a fellowship out of MIT and did a whole bunch of really cool stuff over the years. And then after that, it was really pretty random, I have to admit, just being curious and kind of moving from oil and gas. I had a couple of friends who said they had a startup in biotech. So we did some really cool stuff out of Boston and Harvard with spatial genomics. And then I ended up in robotics out on the West Coast, doing path planning for robots, which was really fun too, because those were very interesting problems. And then now just having a really good time. All these things had kind of like slowly shifted from academic pursuits to more, you know, now we have these problems. How do we deploy them, right? So
Yeah.
even when I first started, I was using like notebooks or MATLAB or and so forth, but very quickly realized it doesn't really work in industry where you have to do code reviews and you have to push stuff into production. So really, the last couple of years, ever since I was with CCG and with Blackstone, like how do you push stuff into production? So I spent so much time learning how to productionize system and some really great podcasts and so forth on I think Ariane Codes, not trying to like drop names or anything, but really getting into his stuff lately and just getting all my team to learn the same things and productionizing systems. So yeah, that's kind of
Very
like
cool.
my random journey.
Very cool. So I think that, to summarize everything, there are a few principles that you maybe naturally deployed or employed, which are curiosity, mentorship in your career, and the ability to, I would call it, push yourself out there, like approach people with questions, inquiries, and just build relationships. Is that right?
Yeah. Yeah, that's the best way to succeed, right? Build good relationships with smart people and be curious and just learn all the cool stuff. There's so much
Yeah,
cool stuff out there.
yeah,
So,
yeah. Very, very cool stuff. Yeah, very
yeah.
cool stuff. And what? So the transformation from academia to industry was natural, or what? How was it for you?
I think initially there was some friction, right? But it
Yeah,
became natural in a way, in the sense that you start doing what you did at academia and you realize it doesn't really work. It is kind of natural, but there's so much friction. You're like, oh, I know how to build this thing by myself. And then, okay, how
yeah,
do I deploy it? How do I deploy?
yeah,
So then you have to start exploring how do I do that? So it's natural through suffering in a way, right? You go
yeah,
and you go learn how to do it because out of necessity, you have to go learn how to do it.
yeah, yeah. If you want to be successful, yes, yes,
Yeah. Yeah.
100%. And do you think that, like, looking backwards into your path, and like, kind of like, let's take the reinforcement learning or dynamic programming type of approach. So they have they're maximizing a utility function or a return function or whatever reward, uh, per step or per iteration, right? If you were, and obviously in life it doesn't work like that. We make mistakes, right?
Yeah.
So if you were now giving advice to your younger self, uh, would you still go through the same process that you went, or would you, let's say, concentrate on data science more, or
I,
uh,
I think the Bayesian approach to life is pretty good. Explore and exploit, right? Explore some stuff and exploit when you get good at something. So
yeah,
I think you hit the nail on the head, right? It's definitely there's not one path to anything. And in
yes,
fact, for the longest time, I didn't really like the term data science, right? Because I really just thought of myself as a mathematician.
yes,
But now it's quite different. The industry is much more developed, and you really even I think it's even evolving now where there is no data science anymore. You have to
Yeah.
really be a machine
Yes.
learning engineer. You have to be able to deploy things yourself.
Yes.
And so it's no longer, I'm a mathematician, I'm this, I'm that. There's so many things that you have to learn to be very effective in
Yeah.
the machine learning space.
Yeah.
But there's so many paths to becoming that, that it's very interesting.
Gotcha. Yeah, I agree. I tend to agree with that. Also, so if you are, let's say I'm starting my career and I
Mhm.
want to be Dr. Alon Arad when I grow up. Okay.
Sure.
Uh, what you do? What would you suggest? What kind of program slash university degree would I pursue right now?
So
Bachelor level. Let's start with that.
I think the best thing you could do is a mixture of mathematics and computer science, right? But
Mhm.
trying to not just do those.
Mhm. Yeah. 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 Yes. Yes. Hmm. Yeah. Yeah. Anything. Yeah. Yeah. Yes. Hmm. Hmm. Yep. Yeah. Yeah. Agreed. Agreed. And so, in theory, or even in practice, one can start from what, high school? If one has, yeah. Nice. Nice. Yeah. Yeah. I know my 11-year-old son is also working around through Python right now. So yeah. So yes. Yes. Exactly. Yes. 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 At least thinking abstractly about the basics, like statements, if then statements, for loops, stuff like that. Yeah. 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 Definitely. Definitely. And okay, so if one has the proclivity for these types of not everyone is was born uh, with a proclivity for math, right? Or for programming, let's say. It's not for everyone, obviously. But if you have it, start early because that will. There is so much you can learn these days, especially as a teenager online, that you will probably never learn in a university even. That's what I think. Yeah. 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 I started programming in basic um, programming language when I was maybe 10 on an Atari machine that has 48K memory, 48 kilobytes memory. And it is part of this built-in test. I remember it to this day. When you restart the machine, first of all, it was like the basic application of this machine was basic. It was load the basic prompt for you. And second, without any that was embedded in the ROM of the machine. And second, it will start by counting each and every byte in the system, and that will take, I don't know, maybe 10 minutes. I never actually timed it, but as a kid, I remember it was, look, come on, load, so I can start programming, right? And yeah, yeah, and Yeah. Yes. Yes. Exactly. Yes. Yes. Exactly. So curiosity, that's a major draw um, towards a successful engineering slash mathematical career in the industry, I would say. And I guess in every field, you can never stop learning. Yeah. And Alon, one of the last questions I have for you is, are you hiring? So for the listeners. Okay, great. And where can people find you? Where is your go to platform? LinkedIn? Okay, great, great. All right. So you heard the man. He's hiring and he's available on LinkedIn. So if you are if you are in the industry now after graduating or before, check out the Walmart website for careers. Right, Alon? Yep. And connect with people, and specifically with Dr. Alon Arad. On LinkedIn. You can never know what a simple hello and a kind gesture can lead to. And Alon, thank you very much for your time. I think we're up for the hour, and thank you very much for your time. I personally enjoyed it very, very much, both the conversation as well as the presentation and lecture. It was fascinating. You're an excellent presenter, and I personally would like to see the relationship between us grow, as well as maybe in the future we can end up doing stuff together. Who knows? Exactly. Exactly. 100. Absolutely, absolutely. All right. So until next time, the listeners, if you have any questions about the presentation or a specific question for Dr. Arad, please comment um, down in the comment section in the video. And have a happy New Year, everyone. Bye bye.